Page 3 and 4 of normal distribution. 24b. We're going to start doing these normal distribution probabilities using a calculator. So, I'm not going to go through this. I'm going to go ahead and do the problem with the calculator, and then you'll see how to use the calculator. Okay? And also, they give you a procedure using the older software, and we probably all have 2.55 software. When you paste, it goes to the regular screen, and then it actually just pastes the command to the screen. It hasn't done the command. So then you need to hit enter to make it do the command. It tells us that the percentage is 11.65% or 0.1165. So we're just going to write here that the probability is 1165. You could write 117 in this case, right? And then we're going to go on to the next one. Now it's going to be 6872. Now I'm going to show you, if you already have done one problem, maybe it's easier if you just go back and type over the limits from before, 70, 74. Now you can just type in 68, and then you can type in 72, because the mean and the standard deviation are the same. And it's going to be 0.131. Finally, it's going to be less than or equal to 65. So there is no lower limit, or you could think of the lower limit as being negative infinity. So let's do this one using the prompt. So it's going to be negative infinity to 65. So how do you do negative infinity? You do negative 1 second double E, which is scientific notation, and we're going to put 99. So that's negative. This is like negative 1 with 0 or 99 zeros after it. It's a really small number. Basically, to the normal distribution function, that's infinity, negative infinity. So the chance is 0.841. Okay. Next one, number 3. A machine produces metal bolts. The length of these bolts have a normal distribution with mean 19.8 and standard deviation 0.3. If a bolt is selected at random from the machine, find the probability that it will have a length of 19.7 to 20. Okay. To kind of figure out if your answer makes sense, sometimes it's good to go ahead and use the picture, even if you're doing it with a calculator. So in this case, the mean is 19.8, so the midpoint is going to be 19.8. Standard deviation is 0.3, so each one of these bars is 0.3 to the right, 0.3 to the left. So this one would be 20.1, and 0.3 to the left would be 19.5. Okay, and let's see what they're asking. They're asking, if a bolt is selected from random, find the probability it will be a length between 19.7 and 20. So 19.7 would be about here, and 20 would be about here. So that would be a pretty good percentage, right? It's kind of in the middle. Okay, so let's go to second distribution. Second distribution, normal CDF, and we're going to put in 19.7 and 20 because those are the lower and upper limits. And then the mean is going to be 19.8, and the standard deviation is going to be 0.3. And that looks like it's maybe going to be like 20% or something, right? Paste. 37.8%. So 0.378. Okay? Make sure you do not put percent because it's already a decimal here. Eels are washed onto the beach after a storm. Their lengths have a normal distribution with mean of 41 and variance of 11. Ooh, this is tricky. They did not give us standard deviation. They gave us variance. Variance of 11 centimeters squared. To find the variance, remember, is sigma squared. So if sigma squared is 11, then what is sigma? You would have to take the square root of 11. Take the square root of 11 by doing second square root, and then I'm going to put 11. Oops. Fat fingered it. which is 3.31. So each one of these vertical lines is going to be 3.31 to the left. So this is going to be 44.31. And this one is going to be 37.69, something like that. Okay, and then they want us to find, if an eel is randomly selected, find the probability is at least 50 long. Wow, 50. 50 is like way over here, right? So it's going to be very small. Let's do that one first. We're expecting a really small number, like less than 5%. Okay, so at least 50, so that means 50 and above. 1 EE 99. 99. The sigma, or the mu, or the mean, is going to be 41, and the sigma is 3.31. Forgot to write that down. I'm going to write it down here. Oops. Okay. Paste. The answer is 3%. 0.00327. Actually, yeah, 0.3%. Then, find the proportion of eels measuring between 40 and 50 long. 40 and 50 long would be about here to about there. So that's a good portion. It's going to be like 50%. So, second distribution, normal CDF. It's going to be between 40 and 50, 41 and 3.31. So the answer is 61.5%, or 0.615. Yeah, so I'm estimated about 50. How many eels from a sample of 200 would you expect to measure at least 45 centimeters in length? At least 45, that would be, 45 is like about here. So it would be like this portion here. Looks like it's maybe like less than 10%. So first we're going to find out the proportion, the percentage that's above 45. Second distribution, normal CDF. So we're going to put 45, and we're going to put 1 EE 99. And then we're going to put 41 and 3.31. And the percentage is 0.113. But they're not asking for a percentage. They're asking for the portion, from a sample size of 200, how many would you expect to be at least 45? So that would be 0.113 times 200 is equal to 22.7. Okay, so you might say 23 because eels can't be fractions. Alright, apples from a grower's crop were normally distributed with a mean 173 and standard deviation 34. So the mean is 173. Standard deviation is 34, so the next step would be 173 plus 34, which would be 207. 173 minus 34 would be 139. And then they say apples weighing less than 130 grams were too small to sell. So that would be about this section here. So that's pretty small. It's going to be like 5 to 10%, right? So let's do second distribution, normal CDF, and we're going to put in weighing less than 130, so that would be negative 1 EE 99, and we're going to put the upper, we're going to put 130, and then the mean is 173, and the sigma is 134. Then we're going to paste it and hit enter again, and it gives us 10.3%, so 0.103. Oops. 0.103 apples were too small to sell. Find the probability that in the picker's basket of 100 apples, up to 10 apples were too small to sell. So actually, let's go back to A. We just found out that this brown section here, which is less than 130 grams, came out to be 10%, 10.3%. Then it comes back and asks us, find the probability that in a picker's basket of 100 apples, up to 10 apples were too small to sell. This is actually a discrete random variable, a binomial probability distribution. Because basically what they're saying is, we got 100 trials. We're picking out 100 apples. And the chance that you get success, which is pick a too small apple, is going to be R equals 0.103. And they're saying, what's the probability that X is going to be less than or equal to 10, because it's up to 10 apples were too small. Okay? So we could use the calculator function for binomial second distribution, binomial CDF, and the number of trials is 100. The P is 0.103, like we just figured out. There's a 0.103 chance that it's going to be too small. And the number of successes is going to be 10 or less. So we're going to put 10 here. And then we're going to paste it. And it's a pretty good chance. It's a 54% chance. 544. Okay. Moving on to number 4. A lot of reading here. So, now we're going to start talking about the z-distribution. The z-distribution is a way of looking at the PDF for the normal distribution that's kind of a standard format. You notice that whenever we drew the normal distributions here, the mean was in a different place, the standard deviation was a different width. Basically, the z-distribution was very commonly used before calculators could figure out normal distributions, because the way we did it in the old days is we looked it up in a table. And they can't like make 50 million different tables for every single combination of mean and standard deviation. But we do know that all normal distributions are the same shape. They're just transformed. So what we do is, instead of having a bunch of different tables, we have one table, which is a standard table, and this standard normal distribution is centered at 0 and has a standard deviation of 1. So the mu is equal to 0, and the standard deviation is 1. And so whenever you get a standard deviation that's not 1, what do? You just adjust your normal distribution so that you shrink it down or whatever so that it looks like the z-distribution, and then you can find the value that corresponds to the one you're interested in. So like for example here, we want 130 grams, and we want a mean of 173. What we do is we just take this distribution, we do some transformations on it, we make it into the z-distribution centered at 0 and the standard deviation of 1, right? And then what we do is we say, oh, well, in this distribution, what does 130 correspond to? And we say, oh, it corresponds to like negative 2.3. And then you look at negative 2.3 in the table to see what the percentage is, for example. That's just an example. Okay, so let's answer these questions. So now z-distribution is not really used for that anymore. Z-distribution is used when you have kind of a weird problem where you don't know the mean and the standard deviation. You need to figure that out, because those kind of problems the calculator doesn't do so well. Okay, the calculator, if given the percentage, the probability, it can figure out the mark on the standard normal distribution graph. if you give it the marks on the normal distribution graph, it can give you the percentage, but if in both those cases, it knows the mean and the standard deviation. So if you don't know the mean and the standard deviation, sometimes you have to use the z distribution to figure out the mean and the standard deviation. Okay? So every normal x distribution can be transformed into a standard normal distribution or z distribution using the transformation. And the transformation is this. It's going to be, you take the original x value, you subtract the mean, and you divide by sigma, or the standard deviation. Where have you seen that before? Well, remember, the standard function for normal distribution is something like this. Something like that, remember? So look, they are doing this transformation. Okay? So actually they are, in the equation, already transforming the x variable into a z variable. So the z distribution has a mean of 0 and the standard deviation of 1, just like we said right there. In fact, the z distribution is distributed as by a normal distribution with a mean of 0 and a variance of 1 squared. Compare the normal x distribution probability density function with the z distribution PDF. Highlight the common elements. Okay, so first we're going to look at these, and we're going to say, okay, well, negative 1/2, negative 1/2, 1 over square root of 2 pi, 1 over square root of 2 pi, e squared, squared. Okay, now we'll highlight some of the different things. Like, look at that. That and that. Okay, z is equal to x minus mu over sigma. And then there's a multiplier here. And there's no multiplier here. Okay, the multiplier is to adjust the height so that the area of the normal distribution always integrates to 1. Okay, so the x distribution has a unique height and width depending on the mu and the sigma. The z distribution, however, always has the same dimensions. Why do you imagine that about 20 years ago the z transformation was always used to transform the x variable into a z variable in order to evaluate the probability? Okay, because no calculators, so only one table with mu equals 0 and sigma equals 1. It's impossible to make a billion tables for every single case, whereas the calculator can maybe create these tables on the fly, so no big deal. Or it does the transform. Page 641. If a z-score of the data is 1.84, then what is the position of x in terms of the mean and standard deviation? Okay, so if the z-score is 1.84, then x minus mu over sigma. So we can solve for x here. So we're going to do 1.84 times sigma is equal to x minus mu. Add mu to both sides. We're going to get 1.84 sigma plus mu is equal to x. This table shows Emma's mid-year exam results. The exam results for each subject are normally distributed with the mean mu and the standard deviation sigma shown in the table. Find the z-score for each of Emma's subjects. Arrange Emma's subjects from best to worst in terms of the z-score. Okay, so we can't compare the results of these scores to each other because, like, what if you have a really hard teacher in one class? What's important is, are you like doing better than most people, right? If you're getting a 90 in the class, but everybody else got a 95, then the 90 is not worth as much, right? So let's take all these scores and we're going to transform them into a standard score. We're going to normalize it, put it at mean of 0 and standard deviation of 1. Okay? So let's see. So this is x. 48. And we're going to transform it into a z-score by doing z equals 48 minus 40 divided by 4.4, for example, right? That's that one. This one would be z equals 81 minus 60 divided by 9. This one would be z equals 84 minus 55 divided by 18. And this would be z equals 68 minus 50 divided by 20. Last of all, this would be z equals 84 minus 50 divided by 15. Okay? So, let's calculate some of these. I'm going to do it with an offline calculator because it's a little faster. Alright, so 48 minus 40 is 8. 8 divided by 4.4 is 1.82. Okay, so that is above average, right? It's 1.82 standard deviations above average. 81 minus 60, 21, divided by 9, 2.33. Okay, that's even more above average. 84 minus 55, 29, divided by 18, 1.61. Okay, 68 minus 50, which is 18, divided by 20, 0.9. 84 minus 50, which is 34, divided by 15, 2.27. Okay, and now we're going to arrange them in best to worst, first through fifth. So this is obviously the worst. It's still above average. It's 0.9 z-score above average, right? Any positive z-score means it's above the mean, but it's the worst one here. The best one is 2.33. The next best one would be 2.27. The next best one is 1.82, and the next one is 1.61. Okay. Moving on to number 3. Consider the normal distribution properties. So here, probabilities, sorry. And here we have the percentages that we have gotten to know on page 1. We got 34, 34. We got 13.5, 13.5. Actually closer to 13.6. We got 2.15, 2.15, which we thought was 2, but it's actually 2.15. And then finally, what we thought was 0.5 is actually 0.13. Okay. Use the diagram to calculate the following probabilities. In each case, sketch the z distribution and shade in the region of interest. Okay. So notice when it's a z distribution, the mean is 0, and each standard deviation is a unit. Okay, so they're all separated just by units of 1. Okay, so what is the probability that z is between -1 and 1? Well, that's easy, right? It's just going to be the two middle probabilities. We already know that 68%, or in this case we could say it's 68.26%, right? Because it says actually each one of these middle sections is 34.13%. Okay. What about z is greater than -1? So that would be equal to 50%, right? Because this whole side is 50%, plus it would also be 34.1% because it's one of the middle sections, which is going to be equal to 84.13%. Finally, the probability between -1 and 0, that would just be this section here, which would just be 34.13%. Okay. It says shade in the region of interest, so I'm going to make a better picture. Okay. So the first one is going to be the two middle sections. So we'll say, oh, well, we're talking about these two middle sections. Okay. The next one is going to be the whole, like half of it, the right half of it, plus this left middle section. Okay? And this one here is going to be the left side middle section. So we'll do that. Okay? And that's it for page 3 and 4.